Hello there, and welcome to the Sleepy Science Society. Tonight, we drift together into the deepest question humans have ever asked. A question so vast that it contains all other questions within it. A question that has captivated philosophers and scientists, poets and children gazing at stars for as long as humans have been able to look up and wonder. Tonight, we explore the universe itself. The word universe means everything. Absolutely everything. Every atom in your body, every breath you take, every spark of light from every star visible and invisible. Every distant galaxy spinning slowly through the void at speeds that would make light itself seem to crawl. Every moment of time that has ever passed or ever will pass. Every thought you have ever had, every dream you have ever forgotten, every possibility that might exist. It is the stage upon which all existence unfolds, the canvas on which all stories are written, the container that holds all containers. And yet, despite living within it, despite breathing it with every moment, despite being made entirely of its substance. Atoms forged in ancient stars billions of years ago and assembled through unimaginable chains of cause and effect into the temporary pattern that is you, the universe remains profoundly, beautifully mysterious to us. We are like characters in a story trying to understand the book that contains them. Like waves trying to comprehend the ocean of which they are momentarily a part. Like dreams trying to understand the mind that dreams them. As you settle into comfort tonight, as your breathing naturally slows and deepens, finding its own perfect rhythm, as your muscles begin to release the accumulated tension of the day one fiber at a time, layer by layer, I invite you to let your mind expand outward beyond the boundaries of your room, beyond the atmosphere of Earth, beyond our solar system and galaxy, into the vast spaces between. Imagine yourself floating in the gentlest darkness, a darkness that is not empty but filled with possibility, with history, with the echoes of creation itself still reverberating through space after nearly 14 billion years. If you enjoy these quiet journeys through science and wonder, these gentle explorations of the cosmos that bring both knowledge and peace, I hope you will consider liking this video and subscribing to our channel. It helps other sleepy souls find their way here, one peaceful night at a time, creating a community of curious minds who find comfort in understanding, who discover that learning about the universe can be both intellectually stimulating and deeply relaxing. But for now, in this moment, all you need to do is rest. Let the concerns of the day fade away like stars disappearing into dawn. Let your thoughts become soft and spacious, expanding like the universe itself. Let us begin this journey together. The universe is almost incomprehensibly large. If you could somehow travel at the speed of light, the absolute cosmic speed limit, the fastest speed that anything can possibly move through space, racing at about 186,000 miles every single second, covering a distance equivalent to circling Earth more than 7 times in the space of a single heartbeat, it would still take you over 93 billion years to cross the observable universe from one edge to the other. Let that sink in for a moment. Light, which can reach the moon from Earth in just over a second, which takes only 8 minutes to travel from the Sun to Earth, would need 93 billion years to traverse the observable cosmos. Light from the most distant galaxies we can detect has been traveling toward us for more than 13 billion years, racing through the void at a speed nothing else can match. And it is only now arriving at our telescopes, at our eyes, carrying information about the infant universe encoded in the wavelengths of photons that have journeyed across unimaginable expanses of space and time. These photons began their journey long before Earth existed, before our sun ignited, before our galaxy had taken its current elegant spiral shape, before any of the familiar constellations had formed. They have crossed distances so enormous that numbers become almost meaningless. Distances that stretch the imagination until it breaks, and we must simply feel the vastness rather than try to comprehend it with logic. And yet, the universe did not begin large. This is one of the most profound and counterintuitive insights that modern science has revealed. According to our best understanding, supported by multiple independent lines of evidence from different areas of physics and astronomy, everything we can see, everything that exists in all directions as far as our most powerful instruments can measure, was once compressed into a space smaller than a single atom, smaller than a nucleus, smaller perhaps than anything we can meaningfully describe using the physics we currently understand. All the matter, all the energy, all the space itself existed in a state of unimaginable density and temperature, a condition so extreme that the familiar laws of physics break down and new, stranger physics takes over. Time itself had a beginning. There was no before, because time, as we understand it, emerged alongside space and matter and energy in that first explosive moment we call the Big Bang. Before the Big Bang, the very concept of before becomes meaningless, like asking what is north of the North Pole. The name Big Bang is actually slightly misleading, a source of confusion that has persisted since the term was coined somewhat derisively by astronomer Fred Hoyle in 1949. The name suggests an explosion like a bomb going off in an empty room, with debris flying outward into pre-existing space, expanding from a central point into a surrounding void. But that is not what happened. That image is fundamentally incorrect. Space itself came into being with a Big Bang. There was no room for the explosion to happen in, no surrounding emptiness for things to expand into. The Big Bang was not an explosion in space. It was an explosion of space itself. It was the beginning of space, the beginning of time, the beginning of physics as we know it, the beginning of causality and change and history. The Big Bang happened everywhere simultaneously, because everywhere came into existence simultaneously. Every point in space has equal claim to being the center of the expansion, and no point has any more claim than any other. When we look out at distant galaxies receding from us in all directions, we might think we are at the center of the universe, but observers in any of those distant galaxies would see exactly the same thing. They would see all other galaxies receding from them, and they would feel equally justified in thinking themselves at the center. The truth is that there is no center, or perhaps more accurately, every point is the center. In the first moments after the Big Bang, in a time interval so brief that it challenges our ability to conceptualize it, the universe underwent what physicists call cosmic inflation. During an almost impossibly short period, lasting perhaps 10 to the negative 35 seconds, a decimal point followed by 34 zeros and then a 1, a duration shorter than any human timescale. By factors that make the comparison absurd, the universe expanded exponentially, doubling in size over and over again at a rate that defies everyday comprehension. In a fraction of a second, far too small to measure with any conceivable clock, the universe grew from smaller than a subatomic particle to perhaps the size of a grapefruit or larger. This might not sound impressive until you realize that doubling something over and over again leads to exponential growth of staggering proportions. If you fold a piece of paper in half 42 times, hypothetically, it would reach from Earth to the Moon. The universe doubled far more than 42 times during inflation. This inflationary period solved several deep puzzles that had troubled cosmologists for years, mysteries about the large-scale structure of the cosmos that seemed inexplicable without some dramatic event in the early universe. It explained why the universe appears so uniform in all directions, why distant regions of space that have never been in contact with each other nonetheless have almost exactly the same temperature and density. Without inflation, this uniformity would be an extraordinary coincidence, like flipping a coin 1,000,000 times and having it come up heads every single time. Inflation explains it naturally. Regions that today are separated by billions of light years, regions so far apart that light has never had time to travel between them, were once close enough together before inflation began to reach thermal equilibrium, to exchange energy and settle into the same temperature. Then, inflation stretched them apart faster than light could travel, preserving that equilibrium across vast distances. The cosmic microwave background radiation that we observe, that faint glow coming from every direction in space, shows this uniformity directly. The temperature varies by only about 1 part in 100,000 across the entire sky, a remarkable consistency that inflation helps us understand. After inflation ended, after that brief moment of exponential growth came to a close, the universe continued expanding but at a more sedate pace. It was filled with an incredibly hot, dense soup of fundamental particles and radiation, a roiling plasma of quarks, gluons, photons, and other particles, all moving at relativistic speeds, all interacting intensely with each other. The temperature was far too high for atoms to form. Electrons and nuclei could not bind together because they were moving too fast, with too much kinetic energy, colliding with photons that had enough energy to tear any forming atoms apart immediately. The entire cosmos glowed with intense radiation, but there was nothing to see it. No eyes, no planets, no structures of any kind. Just a seething sea of elementary particles and light. Uniform and featureless. On large scales, but churning with activity on small scales. As the universe continued to expand, it cooled. This is a fundamental principle of thermodynamics. One that applies whether you are talking about a spray can releasing compressed gas or the entire cosmos. When a gas expands, its temperature drops. The molecules, or atoms, or particles have more room to move in, and as the volume increases, the average kinetic energy per particle decreases, and temperature is just a measure of that average kinetic energy. The same principle that makes a spray can feel cold as compressed gas escapes applies to the entire universe. As space stretched, as the distances between particles increased, As the volume of the cosmos grew larger and larger, the wavelengths of photons stretched along with it, shifting toward longer wavelengths and therefore lower energies. Ultraviolet light became visible light. Visible light became infrared. Infrared became microwave. The universe dimmed from unimaginable brightness, from temperatures trillions of degrees hot, toward something more manageable, though still far hotter than anything we experience in everyday life. About 380,000 years after the Big Bang, a threshold was crossed. This moment is sometimes called the surface of last scattering, or recombination, though the latter term is something of a misnomer since electrons and nuclei had never been combined before. The temperature had dropped enough, to about 3,000 degrees Kelvin, that electrons could finally combine with protons and helium nuclei to form stable atoms. This event changed everything. Before recombination, photons could not travel far without scattering off free electrons. Light would bounce from one electron to another, unable to stream freely through space. The universe was opaque, like trying to see through fog or through the surface of the sun. Every direction you looked would be filled with glowing plasma, a wall of light that you could not see past. But once atoms formed, once the electrons were bound to nuclei, photons could suddenly stream freely through space without scattering. The universe became transparent. That ancient light, released when atoms first formed, when the universe was only a tiny fraction of 1% of its current age, still fills the universe today, stretched and cooled by billions of years of cosmic expansion. We call it the cosmic microwave background radiation, and it carries within it a map of how the universe looked at that distant moment, patterns and fluctuations that tell us about the seeds from which all structure grew. The cosmic microwave background is one of the most important discoveries in all of science, a finding that fundamentally changed our understanding of the cosmos and provided the strongest evidence for the Big Bang theory. When radio astronomers Arno Penzias and Robert Wilson first detected it in 1964, they thought they had found interference, perhaps from pigeon droppings that had accumulated on their horn antenna at Bell Labs in New Jersey. They cleaned the antenna meticulously, removing the pigeons and their droppings, and measured again. The signal persisted. They pointed the antenna in different directions, thinking it might be coming from some terrestrial source or from the Milky Way. But the signal was exactly the same from every direction equally. A uniform glow filling the entire sky. It was not local noise. It was not coming from any particular source. It was the afterglow of creation itself, stretched and cooled by billions of years of cosmic expansion, but still detectable. Still carrying information about the earliest structures forming in space, still whispering secrets about the birth of the universe to anyone with the right instruments to listen. Scientists have mapped the cosmic microwave background with extraordinary precision using successively more sophisticated instruments. The Kobe satellite in the early 1990s made the first detailed maps. The WMAP satellite improved on these dramatically in the 2000s, and the Planck satellite, operated by the European Space Agency and decommissioned in 2013 after years of excellent service, provided the most detailed map we currently have. These maps show tiny variations in temperature, mere millionths of a degree from place to place, but those tiny variations are enormously significant. They reveal slightly denser and slightly less dense regions in the early universe. Places where the matter and energy were not distributed perfectly uniformly, but had tiny fluctuations, ripples, irregularities. These tiny ripples were the seeds from which all structure grew, the primordial perturbations that would eventually become galaxies and clusters of galaxies, and the vast cosmic web. Where the density was slightly higher, even by a tiny fraction of a percent, gravity pulled a bit more strongly. Over millions of years, hundreds of millions of years, that extra gravity drew in more matter, which increased the gravity further, which attracted even more matter, creating a runaway feedback process. This mechanism is called gravitational instability, and it is how stars, galaxies, and clusters of galaxies formed. Small differences amplified over time. Regions that started out slightly overdense became more and more concentrated, while regions that started slightly underdense emptied out, creating the voids and filaments and sheets that characterize the large-scale structure of the universe today. The patterns we see in the cosmic microwave background are directly related to the patterns we see in the distribution of galaxies billions of years later. By studying the ancient light, we can learn about the future that followed it. But here we encounter one of cosmology's greatest mysteries, one that has scientists still searching for answers after decades of research. When astronomers calculate how much gravity is needed to hold galaxies together, to keep stars orbiting at the speeds they observe, to bind galaxy clusters into stable configurations, they find something deeply puzzling. The stars, gas, and dust we can see, all the ordinary matter that emits or absorbs light, are not nearly enough. Galaxies spin too fast. According to the visible matter alone, the outer stars should fly off into space. Galaxy clusters move in ways that suggest far more mass than we can detect through any telescope. Gravitational lensing, the bending of light by mass, predicted by Einstein's theory of general relativity, reveals mass in places where nothing visible exists. Something invisible is providing the extra gravity, holding everything together, preventing galaxies from tearing themselves apart. We call this mysterious substance dark matter, though the name is somewhat misleading. It is not dark in the sense of absorbing light. It simply does not interact with light at all. Dark matter does not emit light. It does not absorb light. It does not reflect light or scatter light or interact with electromagnetic radiation in any way we have been able to measure, despite decades of increasingly sensitive experiments. It does not seem to collide with normal matter in any significant way or with itself. It passes through ordinary matter as if neither type of matter is aware of the other's presence. The only way dark matter interacts with ordinary matter, as far as we can tell, is through gravity. And yet, despite being invisible, despite refusing to reveal itself through any of the normal methods we use to detect things, dark matter dominates the universe's mass. Current measurements based on multiple independent lines of evidence suggest that about 27% of the universe's total energy content is dark matter, compared to just 5% for all the ordinary atoms that make up stars, planets, people. everything we can see with any form of light. Dark matter outweighs visible matter by more than 5 to 1. For every kilogram of ordinary matter, there are more than 5 kilograms of dark matter, invisible and unknown, holding the universe together through gravity alone. How do we know dark matter exists if we cannot see it, cannot detect it directly? We see its effects, its gravitational influence on things we can see. When astronomers observe distant galaxies, they sometimes notice that the light has been bent and distorted in characteristic patterns, arcs and rings of stretched galaxy images. This bending is caused by gravitational lensing, predicted by Einstein's general theory of relativity. According to general relativity, mass and energy curve the fabric of spacetime, creating what we experience as gravity. Light follows the straightest possible paths through this curved space, but those paths appear curved from our perspective, like a marble rolling across a rubber sheet that has been warped by a heavy weight. The amount of bending depends on how much mass is present. By mapping how light is bent, by analyzing the distortions in galaxy shapes, scientists can map where the mass is, even if that mass is completely invisible. These maps consistently show huge amounts of dark matter distributed throughout space in ways that do not match the distribution of visible matter at all. The dark matter forms large halos around galaxies, extends far beyond where the visible stars end, and creates a scaffolding that shapes where galaxies form and how they evolve. One of the most striking and visually compelling examples comes from observations of colliding galaxy clusters, particularly one system called the Bullet Cluster, located about 3.8 billion light-years from Earth. This cluster formed when two massive clusters of galaxies slammed into each other at enormous speeds in one of the most energetic events we know of in the universe. When these clusters collided, the hot gas from each cluster, the normal matter, interacted strongly. The gas clouds collided, friction and pressure slowing them down, heating them to millions of degrees, and causing them to glow brightly in X-rays. But the dark matter, which makes up most of the mass, passed right through without slowing down, because dark matter does not collide with itself or with normal matter. It just kept going, carrying its gravity with it. By comparing where the visible matter ended up, glowing in X-rays in the center of the collision zone, to where gravitational lensing shows the mass actually is, astronomers can directly see the separation between normal matter and dark matter. The mass is not where the glowing gas is. The gravitational center, the place where space is most strongly curved, is displaced from the visible matter, revealing the presence of something massive and invisible. The Bullet Cluster provides some of the most direct and convincing evidence that dark matter is real, that it is not just a modification of gravity, but actual matter that does not interact electromagnetically. What is dark matter made of? This is one of the most pressing questions in modern physics, and the honest answer is that nobody knows for certain. It could be exotic particles that have barely any interaction with normal matter, perhaps something predicted by extensions of the standard model of particle physics, such as supersymmetry. These hypothetical particles are often called WIMPs, weakly interacting massive particles, though the name has fallen somewhat out of favor as experiments have ruled out many of the most popular candidates. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and environmental radiation, cooled to temperatures close to absolute zero, all in the hope of catching the rare occasion when a dark matter particle collides with an ordinary atom. These detectors use various techniques, from liquid xenon that scintillates when a particle passes through it, to crystals of silicon or germanium cooled to temperatures so low that any deposited energy can be detected. Despite decades of searching, despite experiments of increasing sophistication and sensitivity, no confirmed detection has been made. Dark matter remains stubbornly hidden, revealing itself only through gravity, refusing to announce its presence in any other way. Some physicists have proposed that dark matter might not be matter at all, but rather a sign that our theory of gravity needs modification at very large scales. Perhaps Einstein's equations, so spectacularly successful at explaining the solar system, the bending of light around the sun, the precession of Mercury's orbit, the behavior of binary pulsars, break down when applied to entire galaxies and clusters. Perhaps gravity behaves differently on these enormous scales than we currently understand. Modified theories of gravity have been developed, such as MOND, modified Newtonian dynamics, which adjusts how gravity works at very low accelerations, typical of the outer regions of galaxies. These theories can explain some observations, particularly the rotation curves of individual galaxies, but they struggle to explain other phenomena as elegantly as dark matter does. They have difficulty explaining gravitational lensing observations, the cosmic microwave background patterns, the way galaxy clusters behave, and the large-scale structure of the universe. The evidence from multiple independent sources, from different types of observations using different techniques, all points toward invisible matter rather than modified gravity. But the question remains open, debated, contested. Science advances by considering alternatives, by testing ideas against observations, by remaining open to the possibility that our current understanding is incomplete or wrong. Dark matter acts as the invisible scaffolding of the universe, the hidden architecture that shapes where galaxies form and how they evolve. After the Big Bang, after the first moments of inflation and expansion, dark matter began to clump under its own gravity earlier than normal matter could. This is because dark matter does not feel radiation pressure, does not heat up or cool down the way gas does not interact with light at all. While ordinary matter was still too hot and energetic to settle down, still tightly coupled to radiation, still bouncing around in a hot plasma, dark matter was already forming structures, already creating gravitational wells in the fabric of space. These dark matter clumps created deep gravitational potential wells, regions where space was more strongly curved, where gravity pulled more intensely. When ordinary matter finally cooled enough to collapse, when atoms formed and the universe became transparent, that matter fell into the gravitational wells that dark matter had already created, accumulating where dark matter had already gathered, following the invisible blueprint laid down by the unseen majority component of the universe. Over hundreds of millions of years, over billions of years, this process created the cosmic web, a structure so large and so beautiful that it challenges comprehension. The cosmic web is one of the most remarkable features of the universe, and understanding it represents one of the great achievements of modern cosmology. If you could zoom out far enough to see the universe at the largest scales, far beyond individual galaxies or even groups of galaxies, you would see that matter is not distributed evenly. Instead, galaxies cluster along vast, thread-like structures hundreds of millions of light-years long, filaments of galaxies and dark matter stretching across the cosmos. These filaments connect at nodes, dense knots of matter where multiple filaments meet, creating superclusters of galaxies. Between the filaments are enormous voids, vast, empty regions of space containing few galaxies, as if the universe were made of foam, all bubbles and sheets and empty spaces. The cosmic web traces the underlying dark matter distribution, invisible tendrils of mass stretching across the universe, with visible galaxies marking where ordinary matter has accumulated along these dark rivers of gravity. Computer simulations of structure formation, using our best understanding of physics and the properties of dark matter, produce cosmic webs that look remarkably similar to what observations reveal, suggesting that we understand at least the broad outlines of how structure formed even if we do not understand what dark matter actually is. But dark matter is not the only cosmic mystery. In fact, it is not even the strangest thing about the universe. There is something even more mysterious affecting the universe at the largest scales, something that pushes rather than pulls, something that makes the expansion of space accelerate rather than slow down, something that defies our intuitions about how the cosmos should behave. When Edwin Hubble made his landmark observations in the 1920s, working at the Mount Wilson Observatory in California with what was then the largest telescope in the world, he discovered that distant galaxies are moving away from us. This was surprising enough on its own, suggesting that the universe was not static but dynamic, changing over time. But more importantly, he found that the farther away a galaxy is, the faster it is receding. This relationship, now called Hubble's law, provided the first strong evidence that the universe is expanding, that space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. The galaxies are not moving through space. Space itself is growing between them. This distinction is important and often misunderstood. If galaxies were simply moving through static space, there would be a center to the expansion, a point from which everything is moving away. But in an expanding universe, space itself grows, and every observer sees other galaxies receding with no special center point. For decades after Hubble's discovery, cosmologists assumed that this expansion must be slowing down. The reasoning seemed airtight. After all, gravity is attractive. Every piece of matter in the universe pulls on every other piece. All the mass in the cosmos, all the galaxies and dark matter should be pulling back, fighting against the expansion, gradually putting on the brakes, slowing everything down over time. The question cosmologists debated was whether there was enough matter in the universe to eventually halt the expansion and cause the cosmos to recollapse in a big crunch, or whether there was not quite enough mass and the universe would expand forever, just slowing down gradually, asymptotically approaching a state of cold, dark emptiness. Both scenarios seemed reasonable. The idea that the expansion might speed up seemed absurd, a violation of common sense and basic physics. In 1998, two independent teams of astronomers made a discovery that stunned the scientific community and fundamentally changed our understanding of the universe. They had been measuring the distances and velocities of extremely distant supernovae. stellar explosions so bright that they can be seen across billions of light years, across a significant fraction of the observable universe. These particular supernovae, called type Ia, have a useful property that makes them valuable for cosmology. They reach approximately the same peak brightness every time, give or take small corrections, making them excellent standard candles for measuring cosmic distances. A type Ia supernova occurs when a white dwarf star, the dense remnant left behind when a sun-like star dies, accumulates matter from a companion star until it reaches a critical mass threshold. At that threshold, about 1.4 times the mass of the Sun, carbon fusion ignites explosively throughout the star, tearing it apart in a thermonuclear detonation. Because this happens at approximately the same mass every time, the explosions reach similar peak brightnesses. By comparing how bright a supernova appears in the sky to how bright it should be intrinsically based on its known properties, astronomers can calculate how far away it is using the inverse square law of light. What the teams found, after painstaking observations and careful analysis, was deeply shocking. The distant supernovae were dimmer than expected, meaning they were farther away than they should be if the universe's expansion had been slowing down at a constant rate according to predictions. This was not a small discrepancy that could be attributed to measurement error or dust absorption. It was a systematic difference that persisted across many supernovae. The only explanation that fit the data was that the expansion was not slowing down. Instead of decelerating as everyone expected, the expansion was speeding up. The universe was not just expanding, it was expanding faster and faster with each passing moment, accelerating in a way that seemed to violate everything physicists thought they knew about gravity and cosmology. This acceleration requires some form of energy to drive it, an energy that pervades all of space, an energy that pushes outward rather than pulling inward. Scientists named it dark energy, though, as with dark matter, the name reveals our ignorance more than our understanding. We know it exists. We can measure its effects, but we have no idea what it actually is. Dark energy is even more mysterious than dark matter in many ways. While dark matter at least behaves like matter in that it clumps under gravity, forming halos around galaxies and creating large-scale structure, dark energy seems to be uniformly spread throughout space, the same everywhere, unchanging in density even as the universe expands. It does not cluster. It does not vary from place to place as far as we can tell. Instead, as space stretches and the volume of the universe increases, the total amount of dark energy increases proportionally, as if empty space itself carries intrinsic energy. This property is deeply weird, profoundly counterintuitive, and has implications that challenge our understanding of physics. When you double the volume of space, the amount of ordinary matter stays the same, but becomes more spread out, half the density. The amount of dark matter similarly stays constant, but becomes more diffuse. But the amount of dark energy doubles because its density remains constant. More space means more dark energy. As if vacuum itself has energy content. According to current measurements, which come from multiple independent sources, including supernovae observations, measurements of the cosmic microwave background, studies of large-scale structure, and gravitational lensing surveys. dark energy makes up about 68% of the total energy content of the universe. It is the dominant component, more abundant than both dark matter and ordinary matter combined. The universe is mostly dark energy, with a smaller contribution from dark matter and just a tiny fraction of ordinary matter. The atoms that make up everything we can see. And yet, despite dark energy dominating the cosmic budget, we have almost no idea what it is. The simplest explanation, proposed in a different context by Einstein himself over a century ago, is something called the cosmological constant, represented by the Greek letter lambda in equations. Einstein's field equations of general relativity, the equations that describe how mass and energy curve spacetime and create what we experience as gravity, allow for a constant energy density inherent to space itself, a kind of pressure or tension woven into the fabric of the vacuum. Einstein originally introduced this constant into his equations to keep the universe static, to balance gravitational attraction and prevent collapse, because he believed the universe was eternal and unchanging. When Hubble's observations showed the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest blunder and removed it from his equations. But now it seems that Einstein's cosmological constant might have been correct after all, just for different reasons than he imagined. The universe is not static, but space itself may carry energy that drives acceleration. But the cosmological constant, as simple and elegant as it might seem, raises profound and troubling questions that remain unsolved. Why does the cosmological constant have the particular value we observe? A value that seems precisely tuned to allow structure to form and life to exist. If it were much larger, the universe would have accelerated so quickly that galaxies could never form. If it were much smaller or had a different sign, the universe might have collapsed long ago. Quantum field theory, our best theory of how particles and fields behave, predicts that empty space should have energy arising from quantum fluctuations, virtual particles constantly appearing and disappearing on tiny timescales. But when physicists calculate how much energy the vacuum should have based on quantum field theory, they get an answer that is wrong by an absurd margin. The predicted value is larger than what we observe by a factor of about 10 to the power of 120, a 1 followed by 120 zeros. This is perhaps the worst prediction in all of physics, off by more orders of magnitude than any other theoretical calculation in science. Something must be canceling out almost all of the vacuum energy predicted by quantum mechanics, leaving only the tiny amount we detect as dark energy. Nobody knows what that something is, why the cancellation is so precise, or why n equal vacuum energy remains at all. This problem, called the cosmological constant problem, represents one of the deepest mysteries in theoretical physics. Some researchers have proposed that dark energy might not be constant over time. Perhaps it evolves, changing strength as the universe ages, getting stronger or weaker depending on other factors. This would be called dynamical dark energy or quintessence, and it would require new fields or new physics beyond the cosmological constant. Recent observations from an ambitious project called the Dark Energy Spectroscopic Instrument, or DESI, have hinted that dark energy might indeed be dynamic, varying over cosmic history rather than remaining perfectly constant. DSI maps the positions and distances of millions of galaxies across billions of years of cosmic time, using those distributions to measure how the universe has expanded. Some of the early results suggest that dark energy may have been weaker in the past and is getting stronger with time, though these results are preliminary and other explanations are possible. If confirmed, if dark energy really does evolve, this would be revolutionary, requiring us to rethink our entire cosmological model. It would mean that dark energy is not Einstein's cosmological constant, but something more complex, perhaps a new field permeating space, perhaps something arising from quantum effects we do not yet understand. But the evidence is still tentative, and scientists are appropriately cautious, demanding more data and more confirmation before overturning decades of successful cosmology based on a cosmological constant. Extraordinary claims require extraordinary evidence. The combination of dark matter and dark energy, these two vast unknowns, means that about 95% of the universe is made of things we do not understand. All the stars, all the planets, all the nebulae and gas clouds, everything we can see with any telescope operating at any wavelength, all the atoms in your body and in Earth and in everything humanity has ever touched or measured or detected add up to only 5% of the cosmic inventory, a small minority of the total. We live in a universe dominated by mysteries, surrounded by invisible matter, and permeated by invisible energy, both shaping the cosmos in ways we are only beginning to understand. It is both humbling and exciting, a reminder that despite all we have learned, despite the remarkable progress of science over centuries, we have only scratched the surface of what there is to know. Now, let us turn our attention to an even more fundamental question, one that scientists are actively debating and researching right now. A question that might seem settled, but has become beautifully complicated. How old is the universe? For many years, the answer seemed clear and well established. Using measurements of the cosmic microwave background, observations of the motion of galaxies, measurements of the distances to the oldest stars, and the application of our best cosmological models, scientists converged on an age of about 13.7 billion years. Later refined to 13.8 billion years with small error bars. This number became a cornerstone of modern cosmology, taught in classrooms, woven into textbooks, incorporated into our standard narrative of cosmic history. It seemed like one of the settled questions, a number we could be confident about. But recently, over the past few years, new observations have challenged this consensus, and the situation has become complicated in fascinating ways. The James Webb Space Telescope, launched on Christmas Day in 2021 after years of delays and billions of dollars in investment, now the most powerful space telescope ever built, peering deeper into the universe than any instrument before, has sent back images that puzzle and surprise astronomers. Webb can detect galaxies so distant that their light has been traveling toward us for more than 13 billion years, crossing almost the entire span of cosmic history. These are infant galaxies, systems of stars seen as they appeared when the universe was only a few 100 million years old. less than 5% of its current age, existing in the cosmic dawn when the first structures were only beginning to form. The surprise, the thing that has generated controversy and debate, is that many of these early galaxies look too mature, too massive, too well developed for their age. According to the standard cosmological model, the lambda CDM model that has been so successful at explaining numerous observations, galaxies in the very early universe should be small, irregular, messy, still in the process of forming their first generation of stars, with relatively little mass and simple structures. Star formation takes time. Galaxies need time to build up mass, to develop organized structures like spiral arms or bulges. Instead, James Webb is finding the galaxies that appear surprisingly massive and well-developed, with large stellar populations, organized structures, and properties that seem to require billions of years to form, not just a few hundred million. Some of these galaxies are so massive and so mature that they should not exist yet, according to our timeline of cosmic history, according to how quickly we think galaxies can form and grow. Astronomers have called this puzzle the impossible early galaxy problem. One possible solution, proposed by physicist Rajendra Gupta at the University of Ottawa, is radical and controversial. Perhaps, Gupta suggests, the universe is not 13.8 billion years old. Perhaps it is much older, closer to 26 or 27 billion years, almost twice the conventional age. Gupta's model incorporates an old and generally discredited idea called tired light, which suggests that photons lose energy gradually as they travel across cosmic distances through some mechanism other than cosmic expansion, combined with concepts about how fundamental physical constants might evolve over time, an idea explored by physicist Paul Dirac decades ago. If light can lose energy in ways beyond the stretching caused by cosmic expansion, if the photons gradually become redder through some intrinsic process, then our interpretation of redshift would need revision. Redshift is the shift of light toward longer wavelengths, toward the red end of the spectrum, that we observe when looking at distant galaxies. We interpret this redshift as being caused by the expansion of space, with more distant objects showing larger redshifts because space has stretched more between them and us. But if some portion of that redshift comes from another mechanism, from tired light, then objects we thought were distant because of how much space has stretched might actually be even more distant, and the universe might be older than we calculated. This proposal has not been widely accepted by the astronomical community. Many scientists remain deeply skeptical, noting that the tired light theory has been tested extensively over decades and found inconsistent with multiple independent observations, particularly detailed measurements of the cosmic microwave background, the shape and evolution of galaxy clusters, and the way supernovae brightness declines over time. All of these observations favor cosmic expansion as the explanation for redshift rather than any intrinsic tired light mechanism. The mainstream view, supported by multiple independent lines of evidence from different areas of astrophysics and cosmology, still places the universe's age at around 13.8 billion years. Recent studies using larger samples of distant galaxies observed by James Webb Not just the first handful of surprising objects, but systematic surveys of hundreds or thousands of early galaxies have suggested that the extremely massive early galaxies are actually quite rare, unusual outliers rather than typical examples. Most early galaxies observed in larger samples match expectations reasonably well, forming and growing at rates consistent with the standard model. The initial shock, the sense that textbooks needed to be rewritten, may have been an artifact of small sample sizes, observational biases that preferentially detected the brightest and most unusual objects first, and the inherent difficulty of interpreting observations of the very distant universe, where multiple effects can complicate the analysis. Nevertheless, the debate highlights something important about how science works and advances. Science does not progress by ignoring anomalies or dismissing observations that do not fit. It advances by confronting those anomalies, by paying careful attention to observations that do not quite match predictions, by considering alternative explanations, by testing assumptions that had been taken for granted. Whether the universe is 13.8 billion years old or much older, whether dark energy is constant or evolving, whether our understanding of gravity needs modification, the conversation pushes researchers to refine their models, to develop better theoretical frameworks, to build more sensitive instruments, to consider possibilities they might have overlooked. The discomfort of not knowing, of having your certainties challenged, of confronting data that surprised you is exactly where discovery lives. Anomalies have historically led to breakthroughs. The anomalous orbit of Mercury, which could not be explained by Newtonian gravity, led Einstein to general relativity. Unexpected patterns in the spectrum of black body radiation led to quantum mechanics. Perhaps the puzzles we are seeing now, whether about early galaxies or dark energy or the Hubble tension, will lead to something equally transformative. The Hubble tension, speaking of which, represents another fascinating mystery related to cosmic expansion, one that has deepened rather than resolved despite years of additional observations. When cosmologists measure how fast the universe is expanding today using observations of relatively nearby stars and supernovae, techniques based on building a cosmic distance ladder using Cepheid variable stars and type Ia supernovae, they get one answer for the Hubble constant, the number that describes the expansion rate. When they calculate how fast the universe should be expanding today based on observations of the cosmic microwave background, using the detailed patterns in the temperature fluctuations combined with our best cosmological model, they get a different answer. The discrepancy is not huge in absolute terms, only about 5 or 6 kilometers per second per megaparsec, but it is much larger than the measurement uncertainties from either method can explain. Both methods have been checked and rechecked by multiple independent teams, using different instruments and different analysis techniques. Both seem robust and reliable, and yet they disagree by more than can be attributed to random errors. This tension, this mismatch between local measurements and predictions from the early universe, has persisted for more than a decade. At first, scientists quite reasonably suspected systematic errors in the measurements, perhaps subtle problems with how distances are measured using Cepheid variables, or unaccounted for biases in supernova observations, or underestimated uncertainties in the analysis. But as techniques have improved, as more data has been collected, As the James Webb Space Telescope has confirmed and refined distance measurements originally made by the Hubble Space Telescope, the tension has only strengthened and become more statistically significant. Both measurements seem to be correct within their own frameworks, but they point to different values for the Hubble constant. Something is wrong, either with our measurements in ways we have not yet identified, or with our understanding of cosmic expansion itself, or with assumptions built into the cosmological model. Perhaps there is some new physics at play, some feature of the universe we have not yet discovered. Perhaps dark energy was different in the past, behaving in ways that altered how the universe expanded. Perhaps there are subtle effects we have not accounted for. Perhaps our model of the early universe, as successful as it has been, is missing something important. The Hubble tension is exactly the kind of problem that excites scientists and drives research forward. It is not a catastrophic failure of cosmology. The universe is clearly expanding. The Big Bang framework has been spectacularly successful at explaining countless independent observations, and our understanding of cosmic structure formation works remarkably well. But there is a crack in the edifice, a place where predictions and measurements do not quite match, a hint that something is not yet fully understood. Historically, such cracks, such small anomalies, have led to profound discoveries that revolutionized entire fields. The tiny discrepancy in Mercury's orbit, the precession of its perihelion, by 43 arcseconds per century, more than Newtonian gravity predicted, seemed like a small technical problem, but led Einstein to general relativity, one of the most beautiful theories in all of physics. Unexpected observations of stellar spectra, patterns that did not make sense using classical physics, led to the quantum revolution. Perhaps the Hubble tension will lead to something equally transformative. A new understanding of dark energy or modifications to general relativity on cosmic scales, or the discovery of new particles or fields that we have not yet imagined. Or perhaps it will be resolved through more careful measurements that identify subtle systematic errors. Either way, the process of wrestling with the problem, of trying to understand the discrepancy, pushes the field forward. As you lie here in the darkness, breathing slowly and deeply, letting these ideas wash over you like gentle waves, imagine the universe spreading outward in all directions, a vast expansion that has been continuing for billions of years. An expansion that encompasses everything, including the space between your thoughts. Imagine galaxies receding from one another, not because they are moving through space in the ordinary sense, but because space itself is growing between them. New space emerging from the quantum foam, carrying everything along with it. An astronaut could stand perfectly still in intergalactic space, experiencing no acceleration, no force, no sensation of motion, and yet the distance to a faraway galaxy would increase second by second, minute by minute, megaparsec by megaparsec, as new space emerges between them, as the fabric of reality stretches like dough rising in an oven. This expansion has a profound implication, one that reveals the deep connection between space and time. If we run the expansion backward in time like rewinding a movie, everything gets closer together. Galaxies that are now billions of light years apart were once side by side, touching, overlapping. Go back far enough, and they occupied the same point in space. Go back even farther, and everything in the observable universe, every galaxy we can see, every star and planet, every atom, was compressed into a volume smaller than a single atom. This is not just theoretical extrapolation or mathematical speculation. We can see the evidence directly in the cosmic microwave background, the afterglow of the moment when the universe became transparent, the ancient light that still reaches us from every direction. That light comes from everywhere equally, shifted by billions of years of expansion into microwave wavelengths cooled from thousands of degrees to just a few degrees above absolute zero, telling us that the early universe was hot, dense, remarkably uniform, and almost perfectly homogeneous on large scales with tiny fluctuations that would seed all future structure. The uniformity of the cosmic microwave background is striking and initially puzzling. In every direction we look, across the entire sky, the temperature is almost exactly the same, varying by only about 1 part in 100,000, about 10 millionths of a degree. This uniformity across causally disconnected regions so far apart that light has never had time to travel between them, seems deeply mysterious without some explanation. This is part of why cosmologists developed and now largely believe in cosmic inflation, that brief period of exponential expansion in the first fraction of a second. Without inflation, regions of space that are now on opposite sides of the observable universe, separated by 93 billion light-years, would never have been in contact. They would have no mechanism to reach the same temperature, no way to coordinate their properties. It would be an extraordinary coincidence for them to match so precisely. Inflation solves this horizon problem elegantly. It proposes that all the regions we can now see were once close together, in intimate contact, able to exchange energy and reach thermal equilibrium before inflation began. Then, inflation stretched them apart faster than light could travel, preserving that equilibrium across vast distances that would later become causally disconnected. It is an elegant solution, and the patterns we observe in the cosmic microwave background, the specific shapes and amplitudes of the temperature fluctuations, match the predictions of inflation remarkably well, though direct proof of inflation through the detection of primordial gravitational waves remains a goal for future experiments. The tiny fluctuations in the cosmic microwave background, those millionths of a degree temperature variations, those barely perceptible ripples in the ancient light, are incredibly important far beyond their tiny size might suggest. They represent quantum fluctuations from the earliest moments of the universe, random quantum mechanical variations in the density of space that were stretched by inflation to cosmic scales, frozen in place and amplified to become the seeds of all structure. In regions where the temperature was slightly higher, matter was slightly denser. Gravity pulled slightly more strongly. Over hundreds of millions of years, as the universe expanded and cooled, that tiny extra gravity drew in more matter, creating even stronger gravity, drawing in still more matter, in a runaway feedback process called gravitational instability. Small differences amplified exponentially over time. Overdense regions became more concentrated, forming the first stars, the first galaxies, eventually the cosmic web. under dense regions emptied out as their matter was pulled toward neighboring overdensities, creating the voids. The patterns visible in the cosmic microwave background. Patterns that seem random and meaningless to the untrained eye directly map onto the patterns we see in the distribution of galaxies billions of years later. By studying the ancient light with precision instruments, by measuring those tiny temperature variations and analyzing their statistical properties, we can learn about the seeds from which we grew, the quantum fluctuations that eventually became stars and galaxies and planets and life. Let your mind drift now as we continue this journey. Feel yourself floating in the warm darkness of space. The first stars in the universe were different from our sun, different from the stars you see in the night sky. They formed from gas that was almost perfectly pure hydrogen and helium, the primordial elements created in the Big Bang, with virtually no heavier elements. In the modern universe, clouds of gas contain carbon, oxygen, nitrogen, silicon, iron, all the elements forged in earlier generations of stars and scattered into space when those stars reached the end of their lives and exploded. These heavier elements, which astronomers call metals, even though many are not metals in the chemical sense, help gas clouds cool more efficiently, radiating away energy so that the cloud can collapse and fragment into stars. But the first stars, forming from pristine primordial gas untainted by previous stellar generations, had no such help. They could not cool as efficiently. As a result, they were probably much more massive than typical stars today, perhaps 100 times the mass of the Sun, or even more, enormous fusion reactors burning at tremendous temperatures and luminosities, shining with the light of millions of present-day stars. These massive first stars, called Population 3 stars by astronomers though none have ever been directly observed, lived fast and died young in spectacular fashion. The more massive a star is, the faster it burns through its nuclear fuel, the shorter its lifetime. A star 100 times the mass of the Sun might live only a few million years before exhausting the hydrogen in its core and moving on to fuse heavier elements. It would burn helium to make carbon and oxygen, fuse carbon to make neon and magnesium, fuse oxygen to make silicon, fuse silicon to make iron, each stage happening faster than the last, each stage releasing less energy, until finally the core consisted of iron. Iron cannot be fused to release energy. Fusing iron requires energy input rather than releasing it. So when a massive star builds up an iron core, fusion stops. The core suddenly has nothing supporting it against gravity. In less than a second, it collapses catastrophically, rebounding in a supernova explosion that tears the star apart and briefly outshines entire galaxies. These explosions were crucial for cosmic evolution. They took the heavy elements created in the star's cores and outer layers through nuclear fusion, carbon and oxygen, and nitrogen, and silicon and iron, and dozens of other elements, and scattered them violently into space at thousands of kilometers per second, enriching the interstellar gas. The next generation of stars formed from gas enriched with these elements, and gradually, over many cycles of star birth and death, over billions of years, The universe's chemical composition changed from nearly pure hydrogen and helium to the richer mixture we find today. The Sun and its planets formed from gas that had been enriched by countless previous generations of stars. Gas containing about 2% heavy elements by mass, enough to allow rocky planets like Earth to form, enough to provide the raw materials for complex chemistry, and eventually biology and life. Galaxies grew through mergers and collisions, through the gradual accumulation of matter, through the hierarchical buildup of structure predicted by the gravitational amplification of initial fluctuations. In the early universe, galaxies were smaller and more numerous, simpler and less organized. When two galaxies encountered each other, their mutual gravity could pull them together over millions of years, causing them to orbit around each other in an intricate gravitational dance, gradually spiraling inward, eventually merging into a single larger galaxy. Our own Milky Way galaxy has consumed dozens of smaller galaxies over its history, and we can still see the disrupted stellar streams and tidal tails of some of those past meals, stars and star clusters torn from their parent galaxies and scattered across our halo. The Milky Way is currently in the process of cannibalizing a dwarf galaxy called the Sagittarius Dwarf Elliptical, pulling it apart and absorbing its stars over hundreds of millions of years. Billions of years from now, the Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor, currently approaching us at about 110 kilometers per second. The two galaxies will merge into a single enormous elliptical galaxy, a process that will take hundreds of millions of years, will dramatically reshape the structure of both galaxies, and will provide a spectacular show for anyone around to watch it. Individual stars will not actually collide during this galactic collision, because stars are so far apart relative to their size, like grains of sand separated by miles. But the gravitational interactions between billions of stars will fling them into new and chaotic orbits, mixing the stellar populations of both galaxies, trigger waves of new star formation as gas clouds collide and compress, and feed material into the supermassive black holes at the centers of each galaxy, potentially creating brilliant quasars visible across much of the universe. The structure we see today, the cosmic web with its filaments and voids and nodes and sheets, emerged gradually over billions of years as gravity amplified the initial tiny fluctuations present in the early universe. Dark matter provided the gravitational scaffolding, the invisible framework that shaped where matter accumulated. Ordinary matter filled in the details, creating galaxies and stars and planets where the dark matter had created gravitational wells. This process is called hierarchical structure formation, and it is one of the great triumphs of modern cosmology that our models can explain how tiny initial fluctuations grew into the structures we observe. Small objects formed first, stars, and small proto-galaxies, and then they merged to build larger structures over cosmic time. Stars clustered into galaxies. Galaxies clustered into groups and clusters. Clusters gathered into superclusters, and superclusters linked together along filaments stretching hundreds of millions of light years. The process continues today. Structure is still forming. Galaxies are still merging. The universe is still evolving, even though the overall expansion is carrying distant structures away from each other. The observable universe, the region of space from which light has had time to reach us since the Big Bang, the portion of the cosmos we can in principle observe with sufficiently powerful telescopes, contains perhaps 2 trillion galaxies, each galaxy containing anywhere from millions to hundreds of billions of stars, each star potentially hosting planets. The numbers are so large that they lose meaning, becoming abstract, impossible to visualize or fully comprehend. Even if you could visit one star every single second of your life, it would take tens of billions of years to visit every star in just the Milky Way, far longer than the current age of the universe, let alone the countless stars in the 2 trillion other galaxies scattered across observable space. But the observable universe is not the entire universe. This is an important and often misunderstood point. It is only the part we can see, the part from which light has had time to reach us, limited by the speed of light and the finite age of the universe. Light from more distant regions has not had time to reach us yet. The universe could be much larger than the observable part, perhaps vastly larger, perhaps infinitely large, extending in all directions forever beyond the cosmic horizon. We simply do not know, and may never know. What lies beyond that horizon, beyond the farthest galaxies we can see? Perhaps more of the same. More galaxies and stars and dark matter distributed in the same patterns we observe nearby. Or perhaps something entirely different, structures or phenomena completely beyond our current understanding, regions where the laws of physics might be different, or where conditions led to radically different outcomes. We cannot look beyond the horizon by definition, so we can only speculate. Some physicists have speculated seriously about the possibility of a multiverse, a collection of separate universes existing in some sense alongside our own, each with its own properties and perhaps its own laws of physics. In some versions of inflation theory, the inflationary process that shaped our observable universe never completely stops everywhere. Instead, inflation continues forever in some regions of space, a process called eternal inflation, constantly creating new bubble universes that bud off from each other like bubbles in an infinite pot of boiling water. Each bubble would be its own causally independent universe with its own vacuum state, its own value of physical constants, its own particle physics, its own history, completely disconnected from ours. We would be living in just one bubble among countless others, perhaps an infinite number, isolated from them by vast and ever-growing expanses of eternally inflating space. The properties of physics in our bubble, the masses of particles, the strengths of forces, the value of the cosmological constant, might be accidents of how our particular bubble formed, random outcomes of symmetry breaking in the early universe, while other bubbles have completely different properties. The multiverse idea is fascinating and has attracted serious attention from theoretical physicists, but it is also deeply controversial. By definition, if other universes are completely disconnected from ours, if they lie beyond the horizon and can never be observed, if we cannot interact with them or detect them in any way, then it becomes very difficult to test the hypothesis scientifically. How do you confirm or refute a theory about something that is in principle unobservable? Some critics argue that the multiverse is not science at all in the traditional sense, but metaphysics or philosophy, because it makes no testable predictions that could distinguish it from alternatives. Proponents counter that the multiverse emerges naturally from well-established and well-tested theories like inflation, that it is a prediction rather than an assumption, and that it may be possible to find indirect evidence in subtle patterns in the cosmic microwave background or in other observations. They also argue that the multiverse provides a possible explanation for why physical constants seem fine-tuned for life, a puzzle called the anthropic principle. If there are countless universes with different properties, then naturally we would find ourselves in one of the rare universes where the properties allow complex structure, stars, planets, and life to exist, simply because we could not exist in any other type. The debate continues among physicists and philosophers, with no clear resolution yet. Regardless of whether other universes exist, whether our cosmos is one among many or unique and alone, we must confront the question of our own universe's ultimate fate, the final chapter in the cosmic story. How will this immense drama end? The answer depends critically on the properties of dark energy, that mysterious component that makes up most of the universe's energy budget. If dark energy remains constant over time, as the cosmological constant model suggests, if Einstein's simple addition to his equations truly describes reality, then the universe will continue expanding forever, and the expansion will continue accelerating, getting faster and faster, with no end in sight. As time passes, galaxies beyond our local group, beyond the gravitationally bound collection of a few dozen galaxies including the Milky Way and Andromeda, will recede faster and faster due to the accelerating expansion of space between us and them. Eventually, distant galaxies will be receding so quickly that their light can no longer reach us. The light will be stretched to infinite wavelengths, its photons robbed of all energy by the expansion faster than they can make progress toward us. Our cosmic horizon will shrink. Galaxies will disappear from view one by one as they cross the horizon, not because they are destroyed, but because the space between us and them is expanding so fast that communication becomes impossible. In 1 trillion years, observers in the Milky Way, if any intelligent beings still exist then, if civilization somehow persists across such vast timescales, will see only the merged Milky Way Andromeda galaxy, probably called Milkomeda by then, and a few smaller nearby galaxies that are gravitationally bound to us. The rest of the universe will have disappeared beyond the horizon, unreachable and invisible, as if it never existed. Future civilizations might have no way to discover that there was ever a larger cosmos beyond their island of light in an ocean of darkness. They would see no other galaxies, no expansion, no evidence of the Big Bang. The entire rich history of cosmology might have to be reinvented from subtle clues, or might remain forever unknown. As time passes, measured in trillions of years, stars will exhaust their nuclear fuel and die one by one, entire galaxies going dark. Red dwarfs, the smallest and longest-lived stars, burn their hydrogen so slowly that they can continue shining for trillions of years, far longer than the current age of the universe, but eventually even they will fade consuming the last of their fuel and cooling into black dwarfs, cold, dark cinders. Star formation requires fresh gas, clouds of hydrogen and helium that can collapse and ignite fusion. But over time, more and more of the available gas gets locked up in stars, planetary systems, stellar remnants. The supply gradually runs out. Galaxies will grow darker as their stars wink out one by one like lights turning off across a vast city. In about 100 trillion years, give or take a factor of a few, the era of stars will end. The universe will be dark, illuminated only by the faint glow of cooling stellar remnants, filled with black holes, neutron stars, white dwarfs, and cold diffuse gas slowly spreading thinner and thinner. But the story does not end there. The black holes themselves, seemingly eternal, do not actually last forever. Stephen Hawking showed in the 1970s, in one of the most remarkable theoretical discoveries of 20th century physics, that black holes emit radiation through quantum effects near their event horizons. Virtual particle-antiparticle pairs that constantly appear and disappear in the quantum vacuum can be separated by the intense gravitational field near a black hole's horizon, with one particle falling in and the other escaping. The escaping particle carries energy away, and that energy must come from somewhere. It comes from the black hole's mass. Slowly, incredibly slowly, black holes lose mass through this Hawking radiation and eventually evaporate completely. A black hole with the mass of the Sun would take about 10 to the 67th power years to evaporate, far, far longer than the current age of the universe, longer than you can meaningfully comprehend. Supermassive black holes at the centers of galaxies with millions or billions of solar masses would take vastly longer, perhaps 10 to the power of 100 years. A1 followed by 100 zeros, a time span that makes a trillion years seem instantaneous by comparison. But given enough time, in a universe that expands forever, even they would vanish, radiating away their mass particle by particle, leaving behind only a faint glow of particles and radiation spreading through an ever larger volume of space. In the far future, perhaps 10 to the power of 100 years from now or more, when even the supermassive black holes have evaporated, the universe would consist of nothing but an incredibly thin, incredibly cold soup of elementary particles and radiation, spread thinner and thinner by the relentless expansion of space, diluted toward nothingness. Temperatures would hover just barely above absolute zero, just a tiny fraction of a degree, with thermal energy spread so thinly that meaningful interactions between particles would become vanishingly rare. No structures would remain. No stars, no planets, no black holes, nothing complex, nothing to mark time or distinguish one region of space from another. This scenario is called the heat death of the universe, and it represents the ultimate victory of entropy, the final fulfillment of the second law of thermodynamics applied to the cosmos as a whole. The universe would reach a state of maximum disorder, maximum entropy, with no energy available to do useful work, no gradients to drive change, no way for anything interesting or unexpected to happen ever again. It would be the end, not with a bang, but with a whimper, a slow fade into cold darkness and silence. But this is not the only possible future. If dark energy is not constant, if it evolves and grows stronger over time, as some theories suggest, then the universe's fate could be more dramatic and violent. In a scenario called the Big Rip, dark energy would increase in strength until its repulsive effect became powerful enough to overcome not just the cosmic expansion, but also the forces that hold the structures together. First, galaxy clusters would be torn apart as the acceleration overcame gravity on those scales. Then, individual galaxies would be disrupted. Then, solar systems would be ripped apart, planets torn from their orbits around stars. Then, molecules would be torn apart, chemical bonds broken by the expanding space. Then, atoms themselves would be shredded. Nuclei separated from electrons. Finally, in the last instant, perhaps even atomic nuclei would be torn apart, and space itself might be ripped apart at the quantum level, ending the universe in a cataclysm of disruption. The Big Rip would arrive suddenly, perhaps 20 billion years from now, depending on how quickly dark energy strengthens, giving little warning, tearing apart every structure from galaxy clusters down to quarks in the span of a few months or years, ending the universe in chaos and fragmentation. Alternatively, if dark energy weakens over time rather than strengthening, if it eventually becomes insignificant compared to the gravity of matter, or if there is more matter in the universe than we currently measure, then the expansion could eventually slow, stop, and reverse. The universe would begin to contract, the expansion running backward, galaxies rushing back together as space itself shrinks. As the universe collapsed, it would heat up again, retracing the expansion in reverse. The cosmic microwave background would blue shift, becoming visible light, then ultraviolet, then X-rays, heating up everything. Galaxies would merge, stars would collide. Eventually, everything would merge back into a hot, dense plasma, returning to conditions similar to the early universe, approaching a state of unimaginable density and temperature in what is called a big crunch. Some theories suggest that this collapse could trigger a new Big Bang, creating a cyclical or oscillating universe that expands and contracts over and over for eternity, each cycle potentially lasting trillions of years. Each Big Bang emerging from a previous Big Crunch, an eternal cosmic heartbeat. But there are serious theoretical problems with cyclic models, particularly regarding how entropy increases with each cycle, and how to reset conditions for a new beginning, and most cosmologists consider them unlikely given current observations that suggest the expansion is accelerating rather than slowing. The most likely scenario, based on what we know now, given current observations and our best theoretical understanding, is the heat death. Dark energy appears to be approximately constant or changing very slowly. The universe will expand forever, cooling and darkening, galaxies disappearing beyond the horizon, stars burning out, black holes evaporating, structures slowly dissolving into a sea of increasingly dilute radiation and particles until nothing remains but vast, cold emptiness. It is a melancholy ending in some ways, anticlimactic, a slow fade rather than a dramatic finale. The lights going out one by one across the cosmos until only darkness remains. Yet there is something peaceful about it too, something almost appropriate. The universe will have had its time. countless billions of years, trillions of years, of stars and galaxies, of light and warmth, of complexity and beauty, of planets and perhaps of life and intelligence scattered across the cosmos, before finally resting in stillness, before returning to a state of simplicity and uniformity, before achieving a final eternal equilibrium from which nothing can disturb it. Of course, our predictions about the far future rely on our current understanding of physics, and that understanding, as comprehensive as it seems, is almost certainly incomplete. We do not know what dark matter is, what particles or fields compose it. We do not know what dark energy is, whether it is truly constant or evolving. We cannot explain why the laws of physics have the form they do, why the constants of nature take the values they have. There could be phenomena we have not yet discovered, new physics that becomes important on timescales far longer than we can currently imagine. Phase transitions in the structure of space itself, quantum fluctuations that lead to new universes emerging from the vacuum. The universe has surprised us countless times before, confounding expectations, revealing layers of complexity we did not anticipate. It will likely surprise us again, especially as we probe regimes far from current experience. What is remarkable, though truly awe-inspiring when you think about it, is that we can ask these questions at all. We are made of atoms that were forged in stars, elements heavier than hydrogen, and helium created through nuclear fusion in stellar cores, scattered into space by stellar explosions, gathered into a new solar system billions of years later, and eventually assembled through chemistry and evolution and development into thinking, feeling beings capable of wonder and curiosity. We are the universe contemplating itself, a way for the cosmos to know its own story, to marvel at its own complexity and beauty. Every atom in your body, every carbon atom in your DNA, every calcium atom in your bones, every iron atom in your blood, is billions of years old, created in the heart of a star, or in the first minutes after the Big Bang. You are quite literally made of stardust, ancient stellar ash, a collection of particles that have existed since the early universe, temporarily organized into the intricate pattern that is you, that thinks your thoughts and feels your feelings and wonders about existence. And in this brief moment of organization, measured in decades or maybe a century, a tiny instant in cosmic time, you have the capacity to wonder, to question, to understand. You can look up at the night sky and feel the vast distances between stars, sense the incredible spans of space and time. You can learn about galaxies so far away that their light has been traveling since before Earth existed, before our sun ignited, before our galaxy took its current shape. You can try to imagine the Big Bang, the first moments of time, the origin of everything. You can contemplate the fate of the universe billions of years hence, long after our sun has died, long after the Milky Way has merged with Andromeda, in the far future, when perhaps no intelligent beings remain to ponder these questions. You are a small part of something vast, almost infinitesimally tiny in the cosmic scheme, and yet, in your smallness, you contain awareness of that vastness. You can hold the universe in your mind, at least in outline, at least in principle. This awareness is precious beyond measure. For most of cosmic history, for more than 13 billion years, the universe was lifeless as far as we know. Just matters and energy moving according to the laws of physics, atoms and photons and dark matter interacting blindly, following equations, creating structure through the implacable pull of gravity, but with no awareness, no consciousness, no recognition of what was happening. For a brief period, at least on Earth and perhaps in countless other locations scattered across space and time, conditions became right for complexity to emerge. Chemistry became rich enough for self-replicating molecules. Life arose, simple at first, gradually growing more complex. Evolution discovered new solutions, new forms, new capabilities. Eventually, consciousness developed, awareness, the ability to observe and question and understand. And with consciousness came the ability to look outward and inward, to study the cosmos and our place within it, to ask where we came from and where we are going. We do not know if this has happened elsewhere in the universe, whether other worlds have developed life, whether other intelligences exist. It seems likely, given the immense number of stars and planets, given that the laws of physics and chemistry are the same everywhere we can observe. But we have no proof. It is possible that we are rare, that conscious observers are scattered thinly through space and time, separated by such vast distances that they will never communicate, never even know of each other's existence. Each world with life might be an island, alone in the cosmic ocean, developing independently, following its own unique path, facing its own challenges and triumphs in isolation. If that is true, then the act of understanding becomes even more profound, even more meaningful. We are witnesses to existence. The universe would exist without us. Stars would shine and galaxies would spin and space would expand. But there would be no one to see it, no one to appreciate its beauty or unravel its mysteries or write its story. Consciousness is how the universe observes itself, how it becomes aware of its own existence, and perhaps, in some small way that we cannot fully articulate, our understanding matters, not in the sense of affecting the cosmos or changing its behavior, but in the sense of giving it meaning, completing it, allowing it to be known. As you lie here in the darkness, your mind drifting gently towards sleep, like a galaxy slowly dissolving into dark energy, you are participating in something ancient and profound, something that connects you to the deepest rhythms of existence. You are matter that can think about matter. You are atoms that can contemplate atoms. You are energy temporarily taking a form complex enough to ponder energy. You exist for a brief moment in cosmic time, a flicker of awareness in the long unfolding of the universe's story, a candle flame that will eventually go out but that burns brightly while it lasts. And that is enough. It is more than enough. It is everything. The universe is 13.8 billion years old, or perhaps older, or perhaps the question is more subtle than a single number can capture. It is 93 billion light-years across in its observable portion, or perhaps much larger beyond what we can see, or perhaps infinite. It contains 2 trillion galaxies, each with billions or hundreds of billions of stars, giving us numbers of stars that exceed the number of grains of sand on all Earth's beaches. It is expanding, accelerating, evolving in ways we are only beginning to understand. Dark matter shapes its structure through invisible gravity. Dark energy drives its expansion through mysterious pressure. Mysteries outnumber answers. Questions multiply faster than solutions. And yet, despite all we do not know, despite the vastness of our ignorance, we have learned so much, understood so much, pieced together a story of cosmic history that explains countless observations and makes testable predictions about the universe's past and future. We know that everything began from something incredibly small and incredibly hot, a singularity or something like it where physics breaks down. We know that space itself is expanding, carrying galaxies along with it, stretching the fabric of reality. We know that tiny quantum fluctuations in the first instant of time, random variations smaller than atoms, grew over billions of years into the cosmic web, into stars and galaxies and planets, and eventually life. We know that the light we see from distant galaxies is ancient, showing us the universe as it was long ago, allowing us to watch cosmic history unfold. We know that the atoms in our bodies, the carbon and oxygen and nitrogen and iron and calcium and phosphorus, are billions of years old, forged in stars that exploded before our sun was born, scattered into space and eventually incorporated into the solar nebula that formed our solar system, chemically assembled into rocks and water, and eventually living cells and complex organisms. We know that we are connected to everything, part of an unbroken chain of cosmic evolution that stretches back to the Big Bang and forward to an unknowable future, a chain that links us to every star and every galaxy, to the first moments of time and the far distant ending. And we know that the journey of discovery is not over, will never truly be over. New telescopes are being built and planned. More sensitive instruments are being designed. New theoretical ideas are being explored and tested. Each generation of scientists pushes the boundaries of understanding a little further, answering some questions while uncovering new ones, solving some mysteries while discovering new puzzles. The universe keeps secrets, guards them jealously, reveals them only to patient and persistent inquiry. But slowly, step by step, observation by observation, we learn to read those secrets, to understand this vast cosmos we inhabit. If you have enjoyed this journey through space and time, if these ideas have brought you a sense of wonder, or peace, or both, if you have found value in this gentle exploration of the universe and our place within it, I hope you will consider liking this video and subscribing to our channel. It truly helps other people find these quiet explorations of science, these moments of reflection and learning that combine intellectual stimulation with relaxation. You can also leave a comment sharing your thoughts, your questions, or your own reflections on the universe and its mysteries. The community that gathers here in the comments is thoughtful and curious and kind, and I always enjoy reading what people have to say, learning what resonates with different viewers, discovering new perspectives on these eternal questions. But for now, in this moment, let all of this gently fade. You do not need to hold on to any of it, do not need to remember every fact or number. The universe will continue its slow dance through space and time whether you remember these details or not, whether you think about them or not. What matters is that for a little while, for this hour or so, you expanded your sense of what is. You touched something larger than everyday life. You connected with the deep patterns and rhythms of existence, and now you can rest. Now you can let go. Now you can simply be, existing in this moment without effort or thought. Let your breathing deepen, slow, become regular and easy. Feel the weight of your body against the surface beneath you, fully supported, held securely by gravity, that weakest of forces that nonetheless shapes the entire cosmos. Notice how still you can become when you allow yourself to rest completely, when you stop trying and simply exist. The stars continue shining across the universe, though most are too distant for their light to reach us. Galaxies continue spinning, vast islands of stars turning slowly over millions of years. Space continues expanding, stretching and growing, carrying everything along with it toward futures we can barely imagine. And you, here in this moment, are safe and quiet and perfectly allowed to simply be, to rest, to sleep. The universe is patient beyond human comprehension. It has been unfolding for nearly 14 billion years and will continue for trillions more. Passing through transformations we can predict in outline but cannot truly imagine. There is no rush, no need to understand everything tonight, or this year, or ever. You can simply drift, letting thoughts become softer, looser, less defined, like a galaxy slowly dissolving into the dark energy that surrounds it, like stars spreading thinner and thinner through expanding space. Your awareness can gently spread and dissipate, carrying you into sleep, into rest, into the peaceful darkness that holds all possibilities. The darkness around you is not empty, not void. It is filled with possibility, with history, with potential, with the same fundamental quantum fields that fill all of space. You are resting in a universe that is mostly mystery, mostly unknown, and that is not only okay, but somehow perfect. The mystery is part of the beauty. The not knowing is part of the wonder. The questions are as important as the answers. The journey matters as much as any destination. As your mind grows quieter, thought by thought fading away, imagine yourself floating in that gentle darkness. No gravity pulling you down. No edges or boundaries. Just space, vast and peaceful and infinite, holding you softly. You are a small pattern of complexity in an enormous sea of simplicity, an island of order in an ocean of entropy. And right now, that complexity can rest. You can let go of effort, of thought, of the need to understand or remember or do anything. You can simply exist, simply be, simply drift. The universe began in fire, in unimaginable heat and energy, and will end in ice, in cold and darkness and silence. But between those extremes is now this moment, where you exist. And in this moment, all you need to do is breathe, in and out, slower and slower, deeper and deeper, softer and softer, until even breathing fades from awareness, until even your sense of self begins to dissolve, until you slip into the deep quiet of sleep, into rest, into peace. Good night. Rest well. Dream of stars and galaxies if you dream at all. The universe will still be here tomorrow, still vast and mysterious and beautiful, waiting to fill you with wonder once again. Sleep now. Let go. All is well.